So since yesterday you have been learning about how some simple pragmas can change control of your code, data of your code, data scoping, and when you do that, and then you start running application, of course you want speed up, but at the same time you want semantically correct answers. And if you don't get those answers, you probably would like to see what is going on. And one of the issues with debugging OpenMP is because by definition, as you heard all along, that there is indeterminism in the execution model. So it doesn't tell you the order in which your thread is going to be executed, because that gives the compiler and the runtime the flexibility of several types of optimization. So this little talk the talk part is very short. It's about what you should look out or watch out for, and then Jonghyun is going to do a demo, and there is a little hands-on section with GDB. So if time permits, we'll go into that. So one of the most common error you will see, and whenever you open any OpenMP tutorial or page, you will see is a data race condition. And Neil this morning talked about something in superscalar machine environment. Once you start doing more than one thing in parallel, you can run into the situation where you can access and modify, especially in this case data, in an order which is something typically you don't want. So you could imagine yourself, I mean this is a very simple depiction. Just imagine what you are running with 24 threads. And if you are not careful, or if that's not intended, that you would modify a variable x in a way, and you have not declared it private or whatever was the intended use, this thread 3 could read up any value in your code. So you have to be then watch out, okay, if that's really what you want updates in any order, because typically if there is a private shared variable, you may not want to access it like that. And sometimes what would happen is your code would run just fine. Sometimes it would produce different results, and you can see some arbitrary behavior if you run into this data race condition. The other most common error you see is deadlocks. So if you recall what Matt told you yesterday about having critical section, single, atomic, what essentially we do is we try to capture resources in a way where we do lock it for some time. In most cases here we mean by some control part or maybe in some data elements. But you can imagine a situation, and here again it's a very, very simple picture with just 2 threads, but if you have several threads competing for resources, and because the order in which threads are issued and proceed and execute on different cores or on the same core, it's not guaranteed when thread A, thread B, and the other threads would start. They go on locking a resource, and then they wait on some other resource to be unlocked before they can proceed. So you can run into this traffic jam situation. Traffic jams in some cases do get released, but in this case, most of the time you will see a hang and your code won't proceed. So data race condition and deadlocks. Whenever you pick up any book, any tutorial, you will find them. And it's easy to understand, but it's really sometimes tricky if you have large OpenMP sections, and if you are running on multiple threads, these are difficult to identify, because you just can't read through the source and see that arbitrary behavior. So if I look at the example on your left side, the one with critical, do you see the problem? Is it obvious to most of you what is going to be the problem there? Can anyone say something? What is the problem here? Why would we get into deadlock?
Thread which enters the section will just
wait for everyone to do the barrier. So only one thread enters. It's a very sloppy code though. But But that's the idea. And because the OpenMP barrier calls requires all the thread to sync, and only one thread is in that critical section, it can wait for all the threads to sync forever and it won't proceed. A good compiler should be able to identify these type of behavior, but I'm not sure whether all compilers can do that easily. And you see similar kind of behavior when you have a set of operation which is restricted to some threads, not all, and when you try calling something where you want all threads to participate. So there is a typo on my first bullet. You say using barrier in for selected number of threads. Yeah, you should not do it if we want to avoid deadlocks. So you should not use your MP barrier carefully. And if I remember correctly, Matt yesterday mentioned that try not to use these barriers or sync routines. If you try really hard, you can find a way to go around them. But if you do need to use them, just make sure all threads are getting there. Also, Matt mentioned yesterday, and I think this morning Neil also referred, you can call locks function explicitly through OMP API. And try avoiding them as much as possible. And worst, don't try to use lock nesting, because I think you have to be a very sophisticated programmer to get it right, probably. The third, which is set of errors, which I found and I put in here, are not necessarily specific to OpenMP, but you can see them in certain situations. One thing, people call it live lock. Essentially, it's an indefinite loop. So you may have in your while or do loop some conditions that apply to certain number of threads where they go in that infinite loop and other threads wait forever. Because by definition, your OpenMP session is blocking. So you have to watch out for this, that you don't have anything any of your loop exit condition bounded to thread ID where you get into those situations. And then there is other issue where we talk about private and public shared data. But if you start having lots of private large arrays or data structures in OpenMP, you may run into a situation in terms of data replication. And Jeongyeon is going to demonstrate some examples why it could happen. And sometimes you would have memory leaks when you have a dependency on your thread variable. So why do we do debugging and what we get out of it? So you can't read on your favorite text editor what is going on, because there is indeterminism in your code, and there could be a complex code with a lot of dependency. So ideally what you would like to do is use a tool that knows OpenMP, so that can emulate that indeterministic behavior of OpenMP, because sometimes when you insert printf in OpenMP code, because there is a lot of compiler transformation in there, you may change the behavior of code. So it's advisable if you are running into an issue to try out a debugger, because the debugger would help you in finding problems in your multi-threaded code. So there is a cycle. You analyze, you insert breakpoint, you rerun. So it's not typical to OpenMP, but that equally applies here. You want to do your code execution step by step, but what an OpenMP or multi-threaded debugger would let you do, and Jeongyeon is also going to demonstrate that, is how you can examine values for different threads. You can move from one thread to another and see what is going on. You can, of course, like any other debugger, spot at certain places or conditions, and in some cases you can even update values and watch your stack. So most of these concepts are not specific to debugging. Oh, I should have mentioned, and I was rather silly not to mention, that these slides are in a separate printout. Yeah, you should have said that. I think most of you have probably figured out. I was just so excited to get it started and get going. Sorry about that. Yeah, we finished it rather late. So yeah, you want to control the way your program execute, runs. In some cases you can replay things, and you monitor what is going on where you think you are having problems. So you have to narrow it down, and then you control the execution thread by thread or process by process if it's a hybrid code. Stepping and continuing to program, yeah. So there are these features. I mean, debuggers are very sophisticated tools, and you can even look at the assembler level instruction if they do make sense to you, and then you can go on continuing, ending the program. And of course, there are several features to monitor your memory. Jonghyun is going to show several examples of that. So on the previous two slides, it was really not very specific to OpenMP, but we put just in this material to show that what is really unique to OpenMP or multi-threaded applications. As I said, the programming model has this indeterminism by design. So some cases your program would fail, some cases it would run just fine, some cases it would produce different results or something which you don't want. Sometimes it runs with 2 threads, sometimes would not run with 4, or sometimes won't run with 2 either. So the other problem you run into is just because when you use OpenMP, you have compiler transformation, and then you have your OS sort of deciding things on your behalf, because it's a high-level programming model. You do less and you give a responsibility to other tools. What happens in that way is, if you do, like I said, use printf and other type of homemade recipes, then you may not be able to reproduce the bugs the way you want them. So it's a good idea to use debugger rather than your makeshift type of solutions. I mentioned compiler issues because when it goes in, it sees your OpenMP code, it would reorder and do various transformations. We don't need to know what they do, but they can manifest into really complex bugs. And especially when you use data scoping construct, private, shared, first private, last private, you can also run into very interesting and exciting situations. So, which you would only see in multi-threading code, you would not see in other application, in other procedural type of codes. And that's what Jonghyun is going to demonstrate. What are the features which you can use to identify what is happening at certain point of time with all the threads you are using, 2 threads, 4 or more. Then again, like any other, you can do the program execution back and forth and view the memory contents, and like any other debugger, you can go and inspect a core file after a crash, a seg fault essentially. So what are the tools that are available on CSCS platforms? Of course, you have your printf or print or write tools, but we have right now 2 tools. One is Total View. It allows you this debugging the way we are learning mostly today when we have MPI and OpenMP together. So the reason we cannot have a demo for all of you or exercise for all of you is the way the licensing scheme works for Total View is rather complex. So we don't have enough licenses that too many people can try it at the same time. Then we have GDB, of course, but GDB is not really aware of your MPI processor space. So you can do just OpenMP debugging or on a single processor basis. In most cases, you compile with -G compiler flag too, so that the compiler would generate information where you can go back and forth to your source code. This is specific to Cray systems, and I think it's very useful. And some of you may have experienced this thing, that sometime when you run your code for long time, it only fails after 2 hours, 3 hours, or maybe several hours. And what do you do there? I mean, debugging, when you do single stepping and things like that, it's not a convenient way to find out. Debuggers are far more interactive to help you identify this type of crashes. So on Cray system, you can use -gfast, and you have more information available. As Roberto said, docs.com is a very useful resource, and you can even type in the search command Cray fast track debugging and find more about it. So it's not specific to multi-threaded, but I thought we should mention this feature because it may be useful at some point in time. There are other tools, and CSCS is exploring them. And at different point in time, if we feel like there is enough need or there are really powerful features, we could make them available on Rosa and Paloo. And you would find several other utilities from different compiler vendors. In addition to debugging tool, there are tools which help you, which sort of you can consider as proofread your multi-threaded code. So Intel Inspector is an example. It reports potential situation that you may have in your code. And this Roguewig, this company, they have another very nice tool, Thread Spotter. I think it doesn't work right now with MPI, but if you go and read up, they have really very nice feature for multi-thread correctness, for identifying bugs, potential bugs in multi-threaded code. So I'm done here, and on the separate piece of paper, you'll find these links, and we will copy even the slides on the electronic version, so you can just print them out. And on all these sites, whatever I just said is available in far more detail